Thank you everyone for joining us for our presentation of our results. And what I'm doing is that I'm beginning with the best photograph that we received from our camera, which is from after the landing with everything lying on its side on the ground. But it's this presentation event is not about our MaxIQ space data. It's actually about all of your data. What I was thinking is perhaps if you'd like to go around the room and introduce yourselves, because I don't think that everybody has actually met everybody else. Mike Galvin, may we begin with you, please?
Hey folks, I'm Mike Galvin. I'm a staff research engineer at Princeton and also spend about half my time doing space systems education here to our undergrads. And I run our undergrad CubeSat, NanoSat program, um, which was the context in which we participated in this HAB launch.
Wonderful. Thank you. Thank you so much. And Andy, how about you and introducing yourself as well as your team? Andy, I can't hear you at the moment.
Can you hear me now?
Yeah, now we can hear you, yes.
Yes. Sorry about that. Yeah, I'm
Andy,
Andy.
I'm going to jump in also because I'll do the service of also introducing my students Richard and Anuja, who each designed a payload for this launch and will be presenting their results. So we don't have to call on everybody one at a time.
Andy, go ahead.
Can you hear me clearer now?
Yes.
Yes.
Sorry about that. Yeah, sorry, I was double mute. Yeah, I'm Andy Buffler. I'm a professor of physics at the University of Cape Town. We have interest in applied things with radiation, also with high energy neutron metrology, aviation applications, and now maybe space. We generally have we have a cyclotron in Cape Town with 200 MeV neutrons, which gives us a particular advantage in calibrating and characterizing instrumentation for neutron spectra, which has peaks about 100 MeV. So that's our background. In the room also is Tanya Hutton, Dr. Hutton, who's my senior researcher in our group, and Miles Kitson, who will present. He's a PhD student working on compact neutron detectors for high energy neutrons.
Fantastic. Robert and Kevin, I was wondering if you wanted to introduce yourselves.
Sure, I'm Robert Salter. I'm with the contractor with Peraton. We support the different missions throughout the year. I was actually the campaign manager for part of the year there at Fall Fort Sumner. So hello all, and looking forward to some presentations. And then I guess over to VPO Kevin and Andy Hamilton.
Hi, good morning. Andy Hamilton, Deputy Chief of the program. Also have Kevin Dillon on the line with me. We were both out there at the campaign this year supporting the launches, so happy to see this today.
Great. Thank you very much. And Kevin, welcome to the team. Great.
Today, Kevin can't activate his mic.
Okay. All right. That's great. That's absolutely wonderful. Then
Can you hear
I
me?
think yes,
Yes.
now we can hear you. Yes.
Yeah, wonderful. Great. Thank you. Hi, Judy. Hi, Bianca. Hi, everyone.
Hi, Richard.
Hi,
Richard, we were just going around the room doing some introductions. So would you like to introduce yourself and your team, where you're from?
Okay, sure. Great. My name is Richard Nags. I'm from Parklands College, and we're super excited to have been involved in this program. We've been involved with MaxIQ Space since 2022. It's been the most incredible partnership. We've been sending experiments into space, real experiential learning, thanks to Judy and Bianca. And we have a STAR program at our school, Science, Technology, Aerospace, and Robotics program. It's a space science offering. And the vision is to inspire our children to get involved in space, find out more about the space economy, and prepare them for the future. So that's what we are. We're just waiting for Don and Leanne. They're also on the STAR team, and from an educator point of view, to join. But we have about 8 learners in our core STAR team. And then we have a Star Trek team, which feeds into the STAR team. And then we have a lot of space science happening in all of our other subjects.
Great. Richard, thank you very much. Susan, thank you very much for sending through those wonderful slides. And I was hoping that you and your students could introduce yourselves.
Hi, welcome. These are some of my fine students here. We have Aiden Simmons and Sadal. They're going to present their project, the HAB project that they worked on late this spring, and they're looking forward to it.
Fantastic.
We're from Greater Lowell Technical High School.
Yes, in Massachusetts. Wonderful.
Yes, Massachusetts, United States.
That's great. Amanda, hello. Wonderful to see you as well as your students in the background. Welcome back. And I was hoping you would introduce yourself and your team.
Yeah, so I'm Amanda Kruger, and these are students from International Leadership of Texas here in College Station. And we have 4 students representing. The other students are taking a test today that they could not get out of. But because these students behind me are in an advanced math class, they don't have to take the test. So they get to be here with us today. So they're going to be collaborating together to present our data to you guys. It's good to see everybody.
Great. Absolutely wonderful. I think everybody has been introduced. Chris, how about you? I'm not sure if you've been able to introduce yourself.
Yeah, Chris Schwantes with Peraton and NASA Columbia Scientific Wing Facility. I'm a flight project manager and campaign manager like Robert Salter. I think I missed your all's launch, but I was out in Fort St. a brief while. So looking forward to the presentations. Thanks.
Fantastic. Excellent. Thanks so much. Wonderful. So what I was thinking is, without further ado, let's go to our presentations. And here are the payloads. This is a photograph on the right-hand side of the screen. This is a photograph of all of the experiments after they'd been unpacked from the enclosure by Mr. Gorman, who unfortunately cannot join us today, unfortunately. But so this is what it was, everything all together, and what it looked like when it came out of a very dusty enclosure. So what I would like to do is I would first like to hand over to University of Cape Town. Miles, I believe that you're sharing your slides. If you'd like to go ahead.
Yeah.
Is it allowing you to share your slides?
Let me try that. Oh, that's a fun screen. Goodness.
I've made you co-host, so there should be a green square in the middle at the bottom of your screen. There we go.
Okay.
Fantastic.
There we go.
Wonderful. Thank you.
Sometimes Linux doesn't play nicely, but all right. Okay. So hi, I'm Miles Kitson from the University of Cape Town. I will be presenting our work on measuring cosmic radiation with a compact detector. So a quick overview of our detector system. We have incident radiation from cosmic processes, whether that's a neutron or a proton or a photon incident on our detector, which is called a scintillator detector. These radiation deposit energy in the form of flashes of light, which bounce around the detector and then eventually get picked up by a photodetector of some kind. In our case, that's a silicon photomultiplier. And what happens is we've developed a pulse processing board in-house that when we see a pulse from our detector, it sends a signal to the MaxIQ board to count that, and then we count number of detections per time step, second, 10 seconds, and so on. Unfortunately, at this stage, we can't do any discrimination between particles. So for now, it's just counting radiation per second. So this is the sum total of the data that we received from our measurement. We have lovely data for as we go up in altitude, and then at some point our detector turns off. And I'm not sure if this is present with other people, other experiments, if you saw this, but then sometime later, I think during descent, it turns back on again. So we're going to be looking at just the data at the start, so that we have one nice run, because it's hard to interpret the stuff at the end. And so we can have a look at the data, and what we're doing here is we're comparing to sort of an expectation. We're looking at two different simulation packages. One called Carry7A, which is used in aviation to determine the doses received by pilots and flight attendants. And then we're also looking at another simulation software called XPAX, which is a more used more in scientific literature. And here, what's really nice is we can see that the shape, at least, of our data looks about right. As we go up in altitude, we see that our count rate goes up. It peaks around 15 to 20 kilometers, which is expected, and then it goes back down again as we go further up. One thing to note here is that we've fixed the coordinate at the launch location, so we've not taken into account any drift of the detector, but that's something that we're looking into next. But it's an okay approximation for now, having a fixed location. In our simulation, we've only included neutrons, gamma rays, and protons. As you can see in the bottom right, there are many particles that contribute to the dose rate over this altitude range. But we've chosen these as these are the dominant, at least the dominant ones that interact with our detector. We're also aware that our detector is very sensitive, well, it's quite sensitive to the temperature. And so if we look at, on the left here, we put our detector into a negative 80 degrees Celsius freezer to see what happens with the standard radiation source. And we see that our count rate increases by about 50%, 40%, as we get down to minus 50 degrees, which is round about where we get to on the flight. It's actually a bit lower than that. And so on the right, you can see the same data, but here I've plotted the temperature as a function of altitude. And we see the biggest deviation from our simulation is when the temperature is at its lowest. And so we're going to be doing a little bit of work now with this calibration on the left to just pull things closer to simulation, and hopefully that will make it look a little better. That's it for now. I'm not sure how much time I've used, but our next few steps are looking at getting the right GPS coordinates, including the drift in our simulation, correcting for temperature, and then we're busy designing, hopefully for the next high altitude balloon flight or other experiments, a detector that can discriminate between different particles. And this will allow us to better understand in our simulation which things are contributing to what. But thank you so much for the opportunity to present here and for the opportunity to measure on your flight.
Miles, thank you very much. I was wondering, are there any questions for Miles?
Yes, please go for it.
Regarding his presentation and his results?
I would just like to say, beautifully done, succinct and great information. Wow.
So, thank you.
Perfect. Excellent. Wonderful. Miles, thank you very much. And so if we go back to, was there another question? Great. The team from Parklands. Richard, are you going to drive that? Leanne, are you going to drive it?
I will.
Okay. And please let me know if you're able to share your screen.
I will, absolutely. So just to let everybody know, in the Southern Hemisphere, this time of year, all of our students are writing finals. So unfortunately, none of them are able to attend today. However, our team leader, Declan Saw, who's been leading the STAR team since 2022, has prepared a video just to outline the data and everything that we received. The payload that we sent on the high altitude balloon is an exact copy of the one that we want to send onto the ISS. And we're actually very happy that the ISS was delayed because we have picked up some challenges with our data and possibly our sensors. We're not quite sure yet. So it was a blessing in disguise. And I will now play the video and Declan will explain what he found, what the team found. And I just hope the sound works, Judy. So give me a moment.
We'll let you know.
There we go. Okay, I'm going to share sound. Okay. All right, so are you seeing the screen?
Yes.
You're seeing the screen.
Great, so I'm going to play and let me know if you can hear.
Okay, fifth time's the charm for recording this video. I always tend to ramble a fair bit. If Mr. Nags hasn't introduced me, I'm Declan Saw. I'm the current student leader of the STAR mission here at Parklands College. I hope you're all doing well, but onto the analysis. So with the data we received from the HAB mission, we had two primary goals which we wanted to do. Firstly, we wanted to obviously analyze the data. I mean, that's a given. But secondly, we wanted to refine the pipeline we use for analyzing data for the eventual ISS mission, where we're going to attempt to do a vibrational analysis on the ISS to potentially see the possibility of predictive maintenance by recording the vibrations aboard the ISS and how they change over time. Like, imagine a bolt which rattles, and then as it moves further out, it rattles more and more. I mean, that's a simplified example, but that's the core idea. So onto the pipeline we utilized. I don't have time to explain every single component of it, but this is the rough outline where we go from a windowing function from the actual data. We do a windowing function with an anti-alias filter. This is actually the wrong way around. It should be converted to a single magnitude, so x, y, and z to one vector. Then we do the Fourier transform, then a grading filter, a Gaussian low-pass filter, multi-segment parabolic filter. And then finally, the end goal is a vibration frequency change image. Now, if you didn't understand what any of those individual components are, it's not important. Basically, what we're doing is we're just cleaning up the data to make sure it's as accurate a representation as we can get, and then we want to produce a final outcome which looks like this, where we've got a plot of a bunch of Fourier transforms where we can see the frequencies of vibrations at any given moment, and then we can see how these frequencies change over time, like long periods of time. And of course, then we actually implemented that with the code here, where it follows pretty well the, the pipeline we set up. But before I get into the code, very quickly, the structure of our data was like this, where you'll see a lot of overlapping on the plots because each time our chip restarted, it started the counter at 0 again. So you'll see a fair bit of overlapping. Anyway, onto the data. I'm already running out of time. I've got an ad hoc solution here, so I've only got 5 minutes. We've got we calculated the altitude profile, which is horrendously wrong. I can't find out why, because we've tried three different formulas to try estimate the altitude, and each of them keep giving around the range of 1.2 kilometers from the pressure we recorded. So something's wrong there. We've got the pressure the temperature versus the altitude, atmospheric pressure over the entire time. This is where we combined all of the accelerometer readings into one axis and then plotted the amplitude over time, or the magnitude, and then this is the payload's rotation over time. These aren't important right now because those are the individual FFTs. But if I go to the next page, here, we've got the complete vibration frequency spectrogram. So this is showing all of the frequency bins and then how they change over time. Here we've got a logarithmic power versus the frequency for the entire range, because you can see it's relatively homogeneous throughout time, which you expect since it's a payload in the air. And we've got a huge DC offset here, which I assume is probably gravity, since that wasn't removed. And then as you go up in frequency, you see a large dip in the, amplitude of vibrations at that frequency. So this is sort of expected. You don't expect to see many vibrations on a payload suspended in the air. So this is all rather expected, but there's a major issue with this data. There's going to be a quick cut right now, but I've just ran out of time. I'm back now, so yes, I just ran out of time on the recording software I'm using. But yes, so we also produce some, processing logs. And here's where a huge issue arises. And I think it comes due to the actual hardware of the device which we constructed, where I think we were having some sort of error with the I2C lines, where it might have gotten hulled at places where it shouldn't, or we had dry solder joints in certain places with some of the sensors. Because if we take the entire time we recorded for, we've only got 46 minutes of flight time, and it's very unlikely that even a large portion of this is actually in flight, because we see a lot of data where it's just a static reading, gravity, where it's the payload being somewhere and it's in a testing state where it's being powered on and we can just test the payload. And then we also get very weird readings with the temperature, where we see a maximum temperature of 54 degrees and a minimum one of -50. So evidently something is going wrong here. Evidently something's going wrong here. But I think the general idea of the program we've constructed is good. The hardware itself is really where the major pain point is and where we need to improve a lot. And then obviously I've got some things I need to do here. One of the big things we want to do with the code is we want to show the changes throughout the entire pipeline, where you can see, okay, this is what happens when we do the anti-alias filter, this is what happens when we do the windowing function, so on and so forth, for each component, so that we can debug to see if there's any issues and fine-tune a lot of the variables. Like one big variable is how long do we have each of our segments for? Because as you increase the time of each segment, say if we record for 10 seconds and then that's one block, and then 10 seconds and then that's one block, and then we do a FFT on each of these blocks, as we increase that time, we get higher, granularity to the frequency bin size, like 0.01 hertz or whatever, but we also lose a lot of resolution. We get a lot of resolution on frequency, but then we lose a lot of granularity on the changing over time. Hopefully that made sense. I don't have time to record it, unfortunately. Anyway, if you have any questions, I'm certain Mr. Nags has given you my email address. If not, it's dsaul@parklands.co.za is the main one. And of course, we've got the, what do you call it, the GitHub here, where all of the data and all of the code is public. So yes, any improvements, any comments, or any questions, please. It is majorly appreciated, especially as we head now to the time to finalize our payload for the ISS mission.
Great. Richard, thank you very much. I was wondering if at this point there are any questions that Richard, the team
a
can
few
relay.
comments. Just because this will probably also have impacted other payloads. So the temperature fluctuation was not a surprise for me. First of all, it's cold up there once we get up there, but on the ground, never mind, it's maybe not that hot, even though it was a New Mexican summer when we lost it from. But the payload area probably got very hot because the power solution that we chose actually leaked a lot of heat. So that can definitely have impacted, especially the before and after the flight once it was landed. So I just want to say that expect big both negative and positive power fluctuation.
Great. Are there any other comments or questions? Okay, great. Yes, Richard.
If I can say something, Judy. Yeah, we have had the sensor rechecked, and there was some resoldering that was done. But obviously, we're going to start doing a lot of day in the life testing now. We would really love to chat to Miles to get access to that minus 80-degree refrigerator solution that he has, so we can test.
Richard, great, thank you. Richard, while you're there, is the Cape Academy, are they going to be presenting results from their experiments today?
They are also really busy with exams. I haven't had any communication with them.
Okay, great. Okay, wonderful. Perfect. The team from Princeton, Richard and Anuja and Mike, let me hand over to you guys now.
Thanks, Judy. I'll go first with my portion of it. Okay. So the experiment that I was working on, we kind of integrated a bunch of the Max IQ sensors, and then I had my own custom PCB in there as well. So kind of to just see how much data we could get from the Max IQ default sensors, and then also compare that to the data from the PCB. And then there's also a camera on board this one, and the GPS especially. We were hoping to be very interesting. So unfortunately, it looks like most of the data that we have is all from before the launch. So as you can see, the pressure graph, it's all at about 1 ATM. So it's kind of suggesting that this payload wasn't turned on or something happened during the actual launch. The pictures that we have are also looks like from testing beforehand. So it looks like from the watch, it's around Thursday, July 31st, so before the launch. The data for the GPS also didn't happen to get a fix beforehand, and a lot of the data files were empty or corrupt. So yeah, so unfortunately we weren't able to get much information out of this one, but I think Richard was able to get a little bit more, so he can talk to what he has as well.
Yeah, I did have slightly more data. I wouldn't say I have a lot more, but it is good enough, probably. So here's my slide of just most of what I found. The whole point of my PCB was just to, like for the ISS launch, supposed to like characterize just the environment it's around. So this was just like a general test of the readings. And largely we found the temperature inside of the payload itself was high. As mentioned earlier, it's like averaging around 60 to 70 degrees Celsius inside the payload. But if you notice earlier, it does like suggest that it was reading since the launch because of that slight spike from the cold or from 20 degrees Celsius up to the 60. And largely, I think most chips that had altitude and pressure sensors just didn't work after a while. That or we've seemingly broke physics and the world. So here is just a larger blown up screen of the temperature sensing itself. As seen, it fell between 60 and 7 degrees Celsius when it was in flight. And here is a pressure reading of the graph. So the time scale is in like, I believe the 10,000s. So in the first about 50 seconds or so, the pressure reading was like what you'd expect at the ground level. And then afterwards, the pressure did seem to drop and it stayed there the whole time, which is not what you expect from a balloon that's rising. And an interesting thing to note, I just got this information a few weeks earlier about the whole the payload package itself or from inside the balloon would tilt because of how it was launched off. So given that information, I looked at the acceleration on the chip, and this is the horizontal reading of the chip, but this is like the vertical component. You can figure it out. But essentially, you see that in around like the first 30 seconds or so, the chip was laid in some direction, in some one direction, and then rotates after after a minute or so, and it stayed in that rotation as it lifted off. And if you were to overlay this tilting as like a reference point for when the balloon launched off, all the chips lined up with this spike in acceleration in this direction, which means that the chips themselves or the data collected were from at least the beginning of launch. And the chips reading either froze, like all of the readings either froze, or they did get readings, like in the first presentation when we talked about how there was like a gap between the data readings. It could be that the data here was either the whole time before the readings cut off, or it could be just everything added together in addition to when the balloon landed and was resting. Yeah, and also most of like where the spikes froze in conjunction with like the payload tilting probably affected how the readings occurred. So I maybe like the chips at that point experienced some shock and then the data there just froze at that line. Although there are still slight like variations in the readings. So it's either it was reading something, but like the connection wasn't proper, so things froze. That's my running guess, but yeah, that's about it for the readings. We just found we found the temperature readings at least worked, and the rest just froze.
Great. Are there any questions for Richard on that? I have a question or a comment or something. Richard, I think it would be great if you could almost like run the experiment again, but so that maybe just work out, because what you have is there's a number of factors that could have failed. So we could have had a power cut. Maybe the batteries got too cold at altitude, so they stopped performing or something. Maybe there was something in the code. maybe data was being overwritten, etc., etc. Maybe it was the hardware. So it would be really great if maybe you run it again, and what you do is that you only change one of those parameters each time you run it. So maybe what you do is you actually put it in a very warm environment and then throw it into a freezer or something like that. So, to see where it was kind of like where it was going wrong. I think that would be really interesting. And I know maybe one should collect the baseline before the experiment, but even if you collect the baseline after the experiment, then you've got something more or less to compare it with. Anybody else got anything?
Yeah, Judy, I had a
that?
question about this temperature. So maybe to the NASA colleagues, maybe Robert. So the temperature, the log we got for the GPS had the temperature values. Was that I guess was ambient temperature on the side of the gondola, I imagine, because Richard says he's measuring quite a high temperature in our ecosystem in the Max IQ box, and so that might be useful to figure out. So Richard, your temperature values were inside the box, yeah, our box, and you're saying they were quite high, so 50 degrees or something, yeah, and that's all the electronics running, so it kind of kept it quite warm, and that would be quite useful to know. So we should talk and try and get the values that you got. But maybe a question to the NASA people: the temperature log was logging temperature where?
So the temperature log we provided on the flight.rpt is a free air thermistor that dangles below the payload and should not be influenced by the sun or by shade. So it's just essentially the free air temperature of the air surrounding the gondola.
Yeah, thanks.
Great, that is very useful. Thank you very much. Any other questions for Richard? Okay, I was wondering, I haven't seen the team from Nipmuc Regional High School. I was under the impression that Luke was going to present. Luke, are you in the room? Is anybody from Nipmuc in the room? Okay, great. Susan, let's go over to your team. Greater Lowell Technical High School. Would you like me to share the slides, or would you like to share them?
I think, what do you want to do? Do you want to share the slides, or do you want her to share the slides and just say next?
I feel like we should share the slides. That way we can control our pacing.
Okay.
If that's okay with everybody.
Wonderful. Perfect.
Okay. All right. Can everybody see our screen?
Yes, there we go. Yeah. Yep. Just put it into presentation. Yeah, there we go. 100%.
All right. All good. Okay. Good morning, everybody. Well, it's morning for us over here in Massachusetts. My name is Aiden Simmons.
My name is Sadel El-Abeidi.
And we are presenting our NASA HAB project from Greater Lowell Technical High School. So some of the concepts we explored were what we wanted to test with this project was we wanted to look at how air pressure changed sound using a piezo buzzer designed by us. We also wanted to find enhanced acoustic measurement methods and understand how sound behaves in unobservable environments. And we also wanted to tackle concepts of environmental impact and aerodynamics on sound.
So we evaluated the troposphere and the stratosphere. We evaluated the physics of the atmosphere for sound and different types of layers. I'm not going to go super in depth of this because all we did was figure out some sound channeling, some background noises, and how the temperature changes from troposphere to stratosphere.
All right, so our sensor was collecting these parameters. It was collecting our time, the atmospheric pressure, the temperature, the sound pressure, and the humidity. Only about 38 minutes of data were collected. We believe it was because of an intermittent power issue only collected for these periods of time, or this period of time. So as you guys can see, we have 3 approximate measurements for our data points. So our first one is approximately at sea level, and we noticed it had 10,000 or 1,000 things of pressure. And at 4,000 feet, the pressure was dropping to about a certain point of 880 to 875. And then at our final destination, or our final result of testing, our payload was at 42,000 feet, and we noticed it was at 188 units of pressure for about 200 seconds. Here we have some graphs showing some of our data and what we collected so far.
Sorry, I can't see. So the top graph is above sea level, and all of these have a center line of about 900, 1,000, and 150. We have up here 360 above sea level. We evaluated each differently. These aren't all. These are from all the sensors. This is 4,000 above sea level, and below here is 42,000 above sea level. And we see all the frequencies, the sound pressures and the temperatures and the humidity raising above and below sea level.
Here's just some more graphs showing some of the data that was collected, like our sound pressure levels at each of the feet, like 360, 4,000, and 4,200, or yeah. And again, here was the average and the minimum and the maximum of sound pressure at the different heights.
This was sound pressure at 360 feet, and then like the orange one is 360 and the green indicates 4,000 feet. So you can see the different intervals of how sound pressure traveled throughout the time.
And here is another one, or just a bar graph of the exact same example, just so it's easier to see. And this is what we noticed for sound versus humidity at 4,000 feet. We noticed that
the frequency is a little strange here. It's this graph, I noticed it was a little mixed up, and so also our teacher noticed. We want to, I think this is where we got a little screwed up.
It probably went through some clouds.
Yeah.
The humidity changed.
Yeah, the humidity change, you can see the decrease and then the increase of humidity. And that's where it kind of confused me when we were reading these graphs. So I hope I can evaluate sound versus humidity better.
Well, all right. In conclusion, we noticed that moisture is possibly a contributing factor for muffling the sound at 4,000 feet because of things like the clouds it was passing through, most likely, and along with a bunch of other factors. We noticed a range from 16% to 80%, both of them being positive. We also noticed that the maximum decibel level was suppressed by up to 27% by 4,000 feet or higher. The minimal decimal level of values appeared to be less affected. We are not sure why that had happened, but up to 22% reduction in sound overall based on the average values that we discovered. There is a potential for a sound enhancing device based on the data we've collected that we could possibly design and then present to other industries like our school science fair or Skills USA, if any of you guys have heard of that.
This is the conclusion for our project design. The piezo buzzer worked as expected. The code B, the buzzer's audio was strong and everything was working. I wish we started the project earlier because I only had a week. At the end of the school year, I was a junior. I only had a week to finalize all of this. It was super stressful, but I hope the years after us, the kids have more time and they can talk to their group and their mentors more efficiently, so we all can learn and program things a little easier. But we did learn a lot from this. The differences in resulting tones and static decibels was like needed a little more like further evaluation. But the project was a really good stepping stone for our school. We never did anything like this. Well, I never did. So this was very fundamental, and it was really nice to be able to work with you guys and having Zoom calls monthly. It was really nice.
So our next steps for this project is to present this to our school committee, which we have done previously, but we're also going to present them with the results that we've gained previously. We're also going to analyze and create potential models for Skills USA and providing science fairs for applying theory and practice. We may be exploring a possible prototype for multiple engineering competitions to create custom sound amplification devices. And we also hope to plan future missions by increasing and training more Gridalol students to design more custom HAB payloads. This would make a long-term program and keep us at a high STEM level opportunity. Here are some of the photos from from the launch and the flight and what we've noticed. We just want to say thank you, MaxIQ and NASA, very much for the opportunity to further our education and make us better students.
Thank you so much.
Thank you, guys.
Great. Thank you very much. And I completely agree with you. It was a crazy rush, but congratulations on meeting the deadlines. That is the most important thing. When it comes to engineering, it's all about science. It's about meeting the deadlines. Certainly, next time you can certainly improve on it. And you're certainly going to inspire your fellow students to come up with really, really interesting projects. So this was a really interesting project. We none of us knew if it was going to work or have any results at all, but that's okay. Put it on the balloon, see what happens. I was also really fascinated with your data, how the minimums were fairly consistent. It was the maximums. So yeah, I think that's really interesting. But then again, I don't know much about sound and about waves and nature of waves and things. I can imagine that with the humidity, with the medium being more dense, that would definitely affect it. But wow, and it's also a great opportunity to work on that in different circumstances. Hot, humid summers, cold, dry winters, all of that kind of thing. Does anybody else have any questions or comments? Susan, would you like to say anything in terms of, as the educator, as the guide on this journey, this crazy journey? You muted, sorry.
No, thank you so much. I know because my students have been working on the ISS project, this was kind of like as an add-on, and I want to thank Sadal and Aiden and Marcus and the other students for really stepping up to the plate and taking advantage of this opportunity to create a really nice project, which actually has a lot of potential in it for future spin-offs, like maybe creating a recording or the prototype that has been bounced around. Some ideas have been explored. So I think, and there's also other projects that students are interested in creating for use of sensors using the HAB. So I think that you're glad you worked on it, right? So I'm
super glad.
You're super glad. Yes. So thank you so much for this opportunity. And thank you for helping my students and working with my students so they have the deadlines met. Thank you.
Absolute pleasure.
And I must agree. I mean, such fascinating ideas and such fascinating concepts. So well done to everyone, and obviously also to the NASA Salter High Altitude Balloon offering. It's just amazing that we can do this. So well done.
Great. Absolutely. Thank you, Richard. Amanda, I was wondering if your students have if you've analyzed your data and you have some slides to present.
We do. We have some slides to present. So the students do not get as many opportunities to meet together as they would hope due to circumstances that are not their fault. So there is a lot of analysis to still be done, but they did put together a presentation. They're going to come up and take turns presenting at least a broad perspective of what they've seen on the sensors. And just as a baseline for everybody else, these were 7th graders last year. This year, they're 8th graders. And when we endeavored into this, all of the adults and the students have zero coding experience, zero sensor experience. I mean, we were starting from nothing. And there is a beauty in challenging yourself to do something where you're just as likely to fail as you are to succeed. And I feel like that's where you grow and develop as a person. And so I'm just really proud of them for sticking through it and continuing to work through the hardships. We did try to do a custom camera sensor and could not get it to work in time. But I will let them present. Let me get my screen working. Gotta find the correct window. There it is. Okay. Can y'all see the screen?
Yeah, absolutely.
Present mode. Is it full mode for you guys? We're at work now?
Yes, now it is. Now it is. Thank you.
Okay, perfect. Victoria's at first.
Hello, my name is Victoria Benedetti, and I will be discussing the sensors we used, where these may have failed, and our temperature sensor. So this is our table of sensors. We decided to use an acceleration, air pressure, altitude, temperature, light intensity, UV radiation, carbon dioxide, and total volatile organic compounds as our sensors. For our sensor failure, we saw that there was
Sorry, the view screen is in the way. Okay, try that. Is that better?
Yes. Thank you.
Okay.
For our sensor failure, there wasn't any data recorded as the payload descended. We also realized there was multiple gaps in our data. We believe this may have happened because the battery may have died. There may have been a connection or issue with the mainboard or SD card, or the temperatures were too hot as we recorded 140 degrees Fahrenheit or 60 degrees Celsius.
Not yet. Go down to the bottom. There you go.
Nope.
You got it.
For our temperature sensor, we realized the temperature fluctuated between about 20 to 60 degrees Celsius or about 70 to 140 degrees Fahrenheit. As explained earlier, this was because the battery heated up, so it influenced the temperature. We also realized there was a gradual increase before there was a big spike in temperature, and that the temperature went up as the balloon rose in altitude.
Hello, I'm Kate Robichaux, and I'll be going over time and acceleration. In certain unknown conditions, the time started again within 10 milliseconds of the first time stamp. Here's a diagram of that. Overall, the time repeats are all in the same range, but still different sets of number. Every time a new column was created, there was about 1,000 milliseconds that occurred, and our total flight time was about 89 minutes. So for our acceleration, our x-axis, the chips were moving horizontally in either way. For the y-axis, the chips moved horizontally in the opposite way. And for our z-axis, the acceleration was fluctuating, so it was bouncing up and down as it went up. Here's a 3D plot of our acceleration.
Hi, my name is Kinsey, and I'll be going over air pressure, altitude, and the relative humidity sensors. For the altitude sensor, we noticed that it went up, but we did not get any data from the balloon going down, which, as explained before by Victoria, means that the sensor stopped working, but we don't really know why. You can see we have our starting altitude and our ending altitude from our table, and we made a graph, which is represented by the blue line. For our, did I skip one? Yes. For the air pressure, it consistently decreased, going from about 1,000 millibar at ground level to 879 millibar at the highest altitude that we recorded. And for relative humidity, it fluctuated, but there was a point where it dropped significantly, which happened exactly when the temperature hit its max, which we think meant that the air was so hot around the sensor, probably from the battery, that the water molecule capacity dropped. And this is from our table. We have the temperature versus the relative humidity, and we made a graph from that as well. The relative humidity is represented by blue, and the temperature is represented by red.
Hello, my name is Katie Leidendorf. And for light intensity, I saw that at the beginning, the light intensity was very bright. Then it suddenly dropped to about 1.2, and this is probably because before we recorded data, before it was in its container and it went like darker. And for ultraviolet levels, it mainly stayed at 0 for the entire time, except for a small section around the beginning, where it had UV levels of 1.3 to 1.6 megawatts per square centimeter. And for the air quality, see the CO2 levels to the right remained at a baseline of like 400, except for some parts that increased when the temperature hit its max and the relative humidity its lowest. And for the total volatile organic compounds, they basically stayed at 0, except for a couple of spots where it recorded some TBOC. And to conclude, we have some questions. Want to know why when the temperature sensor hit its max, a lot of the other sensors fluctuated. Want to know why the sensor stopped recording, and we want to know why the data came back a bit disorganized. Thank you.
Great. Well done. Well done. That was really terrific. That was a lot of data that was presented there. What I will do is that after this, I will share with everybody a relatively low balloon flight that we did. It went to, I think it was probably 8 kilometers in altitude. That's less than 20,000 feet. And what we found was that we actually went through 2 cloud levels then. And what happens is that the relative humidity really, really increases, especially when you're going through the cloud level. And then when it rises above that cloud level, it just drops to almost 0. And I guess that's because all of the water vapor had actually condensed out into the cloud. And so now you have very, very little moisture in the air than above the cloud, or at least between the cloud levels. So maybe if we were to take the data from the team that had a look at with the sound pressure sensor, they found that when their relative humidity was high, that what it was doing is it was buffering their sound pressure. their decibels, maybe there'll be some correlation with that, and we'll be able to see, because maybe you're actually going through a cloud level without really realizing it. From a temperature perspective, yes, it was a buildup of temperature inside the volume itself, because the temperature should have been decreasing as we increased in altitude, but from a humidity perspective, it was open to the atmosphere. So from a humidity perspective, I would expect that would have equalized somehow. I'm not sure. Maybe somebody else has got a comment on that. Bianca, would you like to make some kind of a comment about the atmospheric pressure at those altitudes is very low. And so when we get a buildup of heat, it's very difficult to actually dissipate that heat because we've got very few air molecules to do so.
Yeah, so obviously this is especially when you get into space, not international in the International Space Station where they locally do have air. But if you launch a satellite, then heat dissipation is very difficult. But I think that with our flight here, one of the things that I talked to Robert Salter about, around the flight was that we used much more energy that we planned to do. I had measured every single circuit and how much energy, and when we try to run this thing here, but I think it probably used double as much energy than to drive the electronics, and I think that there was a lot of heat dissipation in our box doing that. Now it was open, but again, it may be difficult to get rid of the heat, and therefore there was a lot of the electronics here that probably got hot. Now, typically all electronics works perfectly up to 85 degrees Celsius, and we didn't get up there, so there shouldn't have been any problem. But still, I can imagine if it's that hot around the sensors, when we know that at that altitude it's certainly not that hot, and then there can be a lot of misreadings because the heat in the air around the sensors can have given another reading. On the last team here from Texas, they also showed a little bit of data from CO2 and volatile organic compounds. And one of the things that also ran through my mind is that obviously this heat, the source of the heat was in direct connection with our 3D printed box. So it could have also heated up the box enough that it will start off-gassing organic compounds from the plastic. So that could maybe also have influenced the CO2 and TVOC readings. But yeah, the other thing is, of course, that, and I think that, the last team asked why wasn't the data all the way through? So one of the things that's interesting is that there was not everybody didn't have data all the way through. I mean, for example, our project that was fed power and right the same way, we had pictures on our camera from early on, and we also had pictures later on. But there was a period where we didn't have any images, so we were definitely disconnected. There was also a lot of dropouts for a lot of the teams, like you saw when Declan from Parklands, he kind of like said, how they had a lot of files that were written, which just indicate there has been a lot of power outages. So we are not 100% sure why that is. inside the box, there's 4 redundant power supplies to each circuit. So obviously there's only one wire that going from the battery to our circuit, and I can't imagine that that wouldn't have working perfectly. So it could also just be the power distribution itself that might have played a role here, because obviously the individual power circuit for the individual circuit are flying. They will also shut down when there's when the heat gets too high, and then it'll restart again. So that could have been one of the roles that have given somebody some power, maybe even for longer than others, depending on where they were sitting in a rack. So yeah, as I said to Robert from our last flight, we definitely gonna upgrade our power for the purpose of these flights here. So we have the heat dissipation under control. And I also think what we want to do is that we do have a real-time clock. What that means is that instead of relying on the elapsed time from every time you start up, you can read the clock from an external battery-operated clock that will always operate it independent if there's a power failure or not. And that will give you a better chance of reading the time, which is, again, super central. We also had a couple of projects, one from Massachusetts, from Nipmuc, they had a GPS on, and also believe Parkland had one of them that had a GPS on. We haven't been able to see GPS data from any of those two. But that will, of course, also have been interesting to see if we could get data from the GPS, because then we will have kind of like a digital data set we could compare with. Judy, back to you.
Bjarke, thank you very much. Richard's asked a question about the position of one of the UCT payloads, if it was on the top, it being exposed. But I think the one was on the side, but I don't think that one functioned all that well.
What happened was that we had UCT, thanks Richard for the question, UCT had 2 projects, and because they had bigger sensors than this that we allowed for, they were at the end, not exactly the end. Ours was in the one end, but we didn't have any extra sensors, so therefore they could be in a row behind, and they had the sensors there in both ends. And then we also had Montana State University. I don't think they're here today. And they had a project on the side of the box, outside the box. And the reason for that was that they had developed their board for the ISS mission, and that's another core that being used here. So therefore, we managed to put a 3D printed attachment on the outside of the box on the opposite side of the camera, so it's set there. I don't know if they got data at all, but that was the ones that set first out.
Great. Bjarke, thank you very much. Yes, unfortunately, Montana State couldn't join us for today. I'm just having a look at the chat to see if there's any additional questions. I think Richard is asking if we have a systematic issue. Richard, we certainly we need to work on that from our side. As Bjarke mentioned, what we need to do is we need to make sure that we have an uninterrupted power supply, that somehow we make sure that we don't have this tremendous temperature buildup inside the payload bay. So what we found was that last year we insulated the batteries, and we actually had a little heating element for the batteries on board, and that was fairly consistent. So yeah, it's a work in progress. as we go along. But yes, Richard, I see you have your hand up.
Thanks, Judy. I was just wondering, seeing we have Robert Salter here, that was there a systemic problem across the entire high altitude balloon payload? So was there a power failure in payloads other than the MaxIQ payloads?
No, so just to note that, every payload is powered independently. So you had a battery, the other groups had different batteries. So we don't do a shared.
Okay.
So everything was tied into different power units for supply.
Wonderful. Thank you.
Yeah, so Richard, and everybody, the change from last year to this year. Last year we had our own battery. This time the battery was supplied by the NASA Balloon Office here, but it's a dedicated battery for us. And the only reason why we did it this way was that then, every time that there's a flight for we plan to fly, and then everything getting a go and that's canceled, then the battery have to be recharged for the next flight. And we just thought it would be simpler if that power solution was provided by NASA, because they will know, they will be responsible for making it recharge and things like that. So that's the reason why we did it this way around. And I'm pretty sure that, they use the batteries for all the other, the same kind of batteries for all the other flights. So the power issue that was on board here was pretty much our problem. And as I said, what happened is that for each slot, we provide a separate power. So each experiment have their own independent power. There's two sides that they have two different sources of power. And we do that because if there's a short circuit or anything like that, it's not gonna, risk taking the whole project down. So while all that was working beautiful and functioned, we just think that the way that the power distribution boards worked was just that it had to take power from 28 volt down to 3.3, and that process just wasted a lot of power, and wasting power means a lot of heat. And we just need to modify that for our next flight. But what we also kind of like considered was to put in a buffer in the sense of our own battery. So we get power from the bigger battery, and then we kind of like, if there's any issues, we have like, a backup battery if there's any kind of like cabling issue or anything like that. But all that we're gonna fix for our next flights.
Great, Bjarke, thank you so much. And I think before we close out, Robert, I'm not sure if you have any comments or feedback for the group.
No, thank you very much. Excellent presentation for all the science groups, and we look forward to you guys learning lessons and refining your experiments and providing another one for Fall Fort Sumner 2026. Thanks.
Great. Thank you so much, everyone. And yes, we begin the campaign again in January. So I'm looking forward to seeing everybody on the campaign again next year. Thank you all for your presentations, and I will share everything with everyone as well as this video. So for that now, we're going to close out. Thank you so much, and cheers for today.